just how do electric guitar and bass pickups work? I'm Professor Fiore, and I'm going to explain it to you. Welcome to part 2 of the expanded edition of Guitar Pickups and Faraday's Law. Greetings, folks. Professor Fiore back for part 2 of our expanded edition of Guitar Pickups and Faraday's Law. In part 1, and if you haven't seen it, go back and see it. It's important. But in part 1, we talked about all the background in terms of magnetics, the effects of coils of wire and things of this nature, and we introduced Faraday's Law of electromagnetic induction. Now in part 2, I want to pick up from there, given all of this foundational material, and then dive into your basic pickup, right? What's going on here? What's really happening? A couple of things I do want to write down, worth remembering from the first time around. And that is, when it comes to magnetic lines of force, they never cross. And they are closed loops. All right. Okay, so let's take a look at an actual pickup. All right, so this is your basic single coil kind of pickup that you'd have on a Stratocaster. Now, a humbucker is a little bit different, but the underlying theory, at least as far as we're concerned, is the same. So when you take the cover off here, you'll notice there's 6 pole pieces. Actually, in this case, there's 6 magnets, 1 for each string. Get the wrap off of here. And you can see the coil, right? So as I mentioned in the last video, this is very, very fine wire. This is like maybe a number 42 gauge wire. It's magnet wire, meaning it has an enameled coating on it. Because if you didn't have that, if it was bare wire and you just wrapped it, it would just short itself out. So it has this little enameled coating on it, but it takes up much less space than, a normal plastic insulation that you'd have on a wire. So you can get more turns in a given volume, and therefore you get a more efficient coil, all right? But in any case, so like I said, you've got maybe like a 42 gauge wire or thereabouts. So, fine as a human hair. And maybe 5,000 turns, give or take. So when you figure this out, like if you took a voltmeter, right, a standard multimeter, and you measure the DC resistance of this thing, it would probably be 5 k ohms, 7 k ohms, 10 k ohms, somewhere in that vicinity. It's a really high value for a voltage source. And given all of these turns of wire, it's a very high inductance. You might get 1.5, maybe 2 Henrys. Henrys, not millihenries, but Henrys. So that has a huge effect on the impedance of this across frequency. As frequency goes up, the impedance of this thing climbs, right? So it may be, let's say 5K at DC, but when you get up to the upper reaches of the audio region, 10 kilohertz, 15 kilohertz, it could be way, way over that. You could be looking at 20, 30 k ohms impedance on this thing. And that interacts with the input impedance of your amplifier along with the cable, specifically the cable capacitance, and that helps to shape the sound, right? For the good or bad, all right? But the bottom line here is that you have these little magnets. All right, see if I can get one of them out of here. I did loosen one of them. Okay, there we go. So there's one magnet, right? This is just a little magnet. So I got 6 of these in here. All right, 1 for each string. So I'm going to look at one magnet in isolation to see what's going on. Now remember, the voltage that we're going to induce in the coil of wire is N being the number of turns we have, times d phi dt, which is the rate of change of flux. Remember the Greek letter here, phi, stands for the magnetic flux. That's per instant of time. So how quickly the flux is changing in time times the number of turns we have tells us the voltage that we're going to get. All right, that's why we have so many turns, so we can get a decent voltage. All right. Now, we're not getting volts for the most part. We're getting tens, hundreds of millivolts, but that's more than enough for guitars to produce a decent signal for our amplifier. All right. But let's zero in on one of those magnets. All right. So north, south. Now, if you're thinking, hey, wait a minute, mine isn't built that way. Mine is, my guitar pickup actually, instead of having individual magnets, has a bunch of pole pieces. I'll just draw a couple of them over here. In other words, like maybe a soft ferrite material here. And it's sitting on, rather ugly drawing, it's sitting on like a large bar magnet like this. Okay, you can have that too. Ultimately, this simplifies to this, because what ends up happening is these are effectively acting like a focusing device in a way for the magnetic field. If you have access to a Gauss meter, you can do some fun little experiments to show this. And also, some cool things can be explained as far as the shape of the little magnets or the pole pieces that you have. Sometimes these things are chamfered. In other words, if you look closely, it's like the edges are beveled. So, sort of exaggerating this. The pole piece or the magnet might be shaped like this. Okay, it's like, what's the deal with that? Well, if you took a normal magnet, I'm just going to draw our handy dandy bar magnet over here. Okay, and excuse me. You got your Gauss meter out and you measured over here. As I was saying in the preceding part 1 video, maybe you get like 1,000 Gauss right here touching it. As you move away, that falls off really fast. And air, has very high reluctance. It's like high resistance in an electrical circuit. So if you take your meter probe and you put it out here, that could fall from 1,000 down to 50. Okay. But if in between you put in, like a soft iron ferrite material, right? So I'll just put this in like this. Same location. Well, now it's not 50. Now it might be a couple hundred, whatever, all depending on the distances and the precise details of the material. All right. You can play with this in your own lab by taking something as simple as a nail. Okay. You take the nail, and so I can draw this in side view. All right, so here's my nail. Nail comes out, and it's pointy like this. Okay? And you take your probe, and you put your probe right there at the tip. And then you do the opposite, where you put the pointy end here, and you put the top bit over there. If you put your probe here, you're going to measure a much smaller flux density than you would here. Because essentially what's happening is you have the lines of force in here, and the shape of it concentrates that field, right? Remember, air is not permeable as far as magnetic fields are concerned, right? It's very high reluctance. So the lines are going to stay in this material, and they get concentrated. Flux density is exactly that. It's the number of lines, the flux across an area. Well, if you reduce the area down, guess what? Flux density goes up, okay? So that actually does have an effect, right? If you change the shape of these pole pieces or the magnets that you're using, that will actually change the magnetic field, right? The strength of it. But in any case, I don't want to divert too far, right? The big question, of course, is it audible? Well, that's a whole nother thing, right? And if it is audible, is it something that I like? Okay, well, that's an aesthetic. Maybe, maybe not, don't know. But let's get back to our little magnet here, right? So, back to this thing. So simplified, right? We're going to have a coil of wire sitting around this thing. And I'm just going to use blue for lack of anything else. So here's my coil of wire. Again, I'm just drawing this very simply because, this coil is, like I said, it's maybe going to have 5,000 turns. A couple of wires come out here off the coil. And then there is a magnetic field coming out of here. Now I'm just going to show this outer piece. I'm not going to draw it inside like I usually would, just because it gets too busy. All right. So that's essentially what we're looking at. Now there is a string. Now we can draw the string in one of two ways. You can either draw it head on, like this. Tell you what, just to make this, I'm going to do something else. I'm going to change the color on this because I don't have enough colors. So you could draw it head on, all right? So it's like I'm looking down the neck. That's what I'm seeing. There's my string. Or you could draw it from the side, right? If I'm looking across the guitar, and you get something like this, all right? So in the first video, I was talking about what happens when there's an interaction between the magnet and some ferromagnetic material, right? We had a little bar, we moved the bar around, and we saw how that worked the field, all right? So there's a couple things going on here. First of all, got to get the right color. First of all, right, some of these lines are going up like this. Okay, and this is a ferromagnetic material. If you strung an electric guitar with a classical guitar strings, with nylon strings, the pickups aren't going to work. Right? The strings have to be ferromagnetic. So as this moves, right, you pluck the string and now it's going to vibrate. That distorts the field. The field is cutting the coil. And therefore, according to Faraday's law, we induce a voltage in the coil. All right? Now, you will hear people say, no, 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 no. What actually happens is the magnet magnetizes the string, and it's the string that does all the action. In other words, there's this field on the string, and that's really what's doing the action. Okay? And I've seen the following argument. People will say, let's see, let me use the same color here. They'll say, yeah, here's the side view of the string. It's like the string turns into a bar magnet, all right? They're saying, it's like a bar magnet. And then, it has a field and, it fluctuates, right? And that cuts these coils and off we go. Well, no, that's impossible, okay? It's not going to behave like a bar magnet. Forget about that. That's wrong. There's other wrong things about that, but I don't want to digress too far. What can happen is that the string itself, because lines are going through it, there's going to be some retentivity in that material. It will create its own field, all right? So to kind of zoom in on that, here's your string. And we've got, these lines of force coming up, what I'm drawing here. And then this thing will create its own, which I will draw here. Not like this. Okay? This orientation, not this crossways orientation. This is a possibility. All right? Okay, so now you pluck the string and the string vibrates, all right? Do these lines cut those coils? Lines never cross. So if this thing is vibrating, if there's a field here, right? You want these lines to cross these other lines? Not going to happen, okay? That does not happen. What does happen is that these lines can interact. In other words, these lines can push against those lines, kind of like the example I had of a couple of different magnets, right? In part one, we had the example of, well, let's take two magnets and face them. So like this is north and this is north. So now this thing is trying to produce a field like yay, and this one's going like this. You try to push them together, what happens? Those lines don't cross. They like squish against each other, and you get this kind of effect. All right? And of course, you feel that. You take two magnets in this orientation, and you try to push them together. You feel that, right? The interaction of those two fields as they're squishing together. So you can have that effect along with the original effect that I was talking about. The question is, how big is that? Well, that will depend on a couple of things. It'll depend on how big this field is, how strong is this field, and the nearness to the coil. All right? Got the wrong thing here. Okay. So, what do you do in a case like this? Well, I know what I do. Is I go in the lab and I start measuring stuff. All right? So I made up, because I wanted to know, numbers. I think it was Lord Kelvin who said, if you haven't quantified, in other words, if you haven't measured characteristics of a phenomena, then you have only a partial and sort of lackluster knowledge of it. All right. So anyway, I built a little apparatus. Pretty easy, actually. In my Science of Sound class, we have an experiment on tension strings. So basically, we take a piece of piano wire, and it sits on this apparatus, and we put a mass on the end of it. There's a little pulley affair, and we can very accurately get the tension on the string, and we can pluck the thing. We have a pickup and oscilloscope. We can see the waveform, measure the frequency, and it's a lot of fun. Okay, so basically, I just take that, and I take a pickup, like yay. And actually, what I did, it wasn't this pickup; it was a different pickup. But I took all of the pole pieces out, all the little all-no-go magnets in that one. I took them all out except for one. And I actually bored out the hole so that it was easy for me to take the magnet in and out. So there's this nice coil of wire and one magnet. Okay, so I can just focus on this. And then I just position it over the piano wire, right, over the string. Okay, so along with that, I get out my Gauss meter and I take some measurements. So what do we get? Well, right at that magnet, if I take the Gauss meter and I put it smack dab on there, right? So there's my probe. I'll just pretend this is the probe, right? Bump, go right on the magnet. I might get like 1,000 Gauss on this thing. Now, that, of course, is not what's at the string. So if you position this at the string, so I'll say the vibrating string is, and I'll just kind of draw it wavy to indicate it's vibrating, right? If I take the probe and I put it over here, because of the intervening distance, that's going to drop down considerably, right? So, you might get like 50, 60 Gauss, right? I mean, it's going to depend on exactly where you put your probe, right? But the important thing is it's considerably smaller, all right? Now, I said that you have this magnetic field. Here's the original drawing I had, right? And here's the string. So when those lines of force come up, oops, get the right color. When those lines of force come up, and we produce this little bit of magnetic field on the string itself, what do we wind up with? All right, that depends on the retentivity of that material. How big is that? So, I leave the string here, and then like I said, I took this, I was able to pop the magnet out real quick, right? Pop it out, and what's the residual on the string? Well, obviously it's less than what was there originally, but the residual is somewhere around like, 5 to 10 Gauss max. It's really small, right? Compared to, you know, what you're looking at as far as coming out of the magnet here. So the experiment was actually pretty simple. If the idea is that it's the magnet that controls this whole thing, in other words, the magnet is only there to magnetize the string. So once the string is magnetized, I don't need the magnet anymore because it's the string's field that's doing everything, right? That's the argument that you hear. The string's field is doing everything. And I've literally heard people say, yeah, you could get rid of that magnet, okay? So here I am in my little thing. Actually, this is sitting above the string. So it's like, this is the string and here's this. And I can just reach in, and I just had a little thingy attached to it, so I could just rip the magnet out. You do that, and guess what? Signal disappears. Big surprise, right? It's like, there's a signal. Rip the magnet out, nothing. I mean, it goes to nothing. You put it back in, and it's still vibrating, right? You know, whatever the, you know, standard, you know, sort of residual ring out was on that string. Put it back in, you see it, pull it out, it's gone. Do this all day, right? Did it like, you know, a dozen times. So you can't say it's just the magnetism of the string in this case, right? There is, like I said, some effect with the existing magnetic field, right? It is possible, you know, because being the curious kind of guy that I am, I wanted to see, well, how far can you take this? So what I did is I took the magnet and I blocked it right onto the string. So what does that do? Well, remember what I said. You know, by itself, this thing was like 1,000 Gauss. So you attach that right to the string, and now you're going to magnetize the string at a much, much greater level than just going through this, all of this air, right? The high reluctance of the air, right? So now instead of having, 50 or 60 Gauss that's going to try and magnetize the string and giving me a residual of maybe 5 or 10, now I'm going to take the magnet, put it right on there at 1,000, and now my residual, right, what I come back and measure, is around like 100 Gauss. In other words, it's up around where this basic system is, okay? Under that circumstance, now you can actually remove the magnet and get signal. That makes perfect sense, right? Because now you've got this string magnetized order of magnitude higher than what it would be like this, okay? So you might say, well, are you saying that I could touch my strings with a magnet and then I could like remove the magnets in my pickup and it would still work? Yeah, it would, but it's not practical. I mean, like, who would want to do that? And secondly, all somebody has to do is come by with a magnet and touch your strings, and they'll demagnetize everything, and you got nothing, right? You got to have the magnet there, okay? So, other things I did. I pulled the magnet, put the magnet underneath the string, right? Because right now I got the string, my little jig there is above, okay? Now I can take that out and put it underneath. So I've got my coil of wire up here. The vibrating string is my hand, right? So I got the coil of wire up here, and the magnet powering the whole thing is down here. Well, guess what? That's enough to get a signal. Now, the signal is not the exact same size, but again, that has a lot to do with exactly how you space things. And I wasn't going to sit there with a caliper and try to get this thing exact. I'm looking for general process, okay? So, bottom line here is you have this magnet or a pole piece. Like I said, if you had the bar magnet underneath, it's the same idea. And there is this coil of wire. Oops. Let's use a different color here. And there is this coil of wire sitting around here. 5,000 turns, whatever it is. And what ends up happening is, as this vibrates, as the string vibrates, there is this field from the permanent magnet. The string moves, it distorts this larger field which is cutting the coil, right, cutting the lines of force. And at the same time, there is a much, much smaller field developed around the string itself, which is sort of aiding this process by helping to push against this field from the top. Okay? How much? How much is much? Well, the basic idea that you don't need a magnet at all is not borne out by the evidence, right? Unless, like I said, you do something really extreme where you purposely try to magnetize the string at a much, much greater level than what would be the case by having a string at a normal distance from the pole piece or the magnet. All right? So that's essentially what's going on. Now, there's a lot of subtlety in here. How strong is the magnet? Is it shaped interestingly? Does it have that sort of beveled edge? What's the spacing on the string? What's the retentivity of the material in the string? The actual construction of this varies a bit. And then, there's also a question of, maybe you have a vintage pickup. It's been around for a long time. There could be issues like microphonics where, if there's an acoustic signal, it could literally shake the coil because it's not potted correctly. It's old and it's kind of, the wires are a little loose. And that acoustic signal can actually shake the coil and produce signal. So that might actually enhance feedback. That might be something that you like under certain circumstances. All right. So there's a lot of variables in here. And ultimately what really matters is, what are your ears telling you? Right? You monkey with variables. I mean, if you're one of those people who likes to design your own pickups, you monkey with the variables and you listen and you monkey again and you listen, right? And you go back and forth until you get what you like, right? I mean, that's ultimately what aesthetics is about. You don't just sit there and run through some equations and say, burp, 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 and I'm done, right? It's not like designing an amplifier where you say, well, I need a certain frequency response and I need, a certain noise level and distortion and so forth. I can do a lot of those calculations and get, 90% of my work done and then give it, the final golden ear test. But this kind of stuff, guitars are fun because people like distortion in their guitars, okay? But ultimately, this is the physics that controls those pickups. Now, if you're going to say, hey, I got piezoelectric pickups in my guitar, that's a whole nother animal, okay? All right, well, I hope you've enjoyed this. Until next time, this is Professor Fiore saying, take care and have a good one.